Welcome to the third lecture on work, energy, and power. And you're probably thinking, oh, where are the equations for this one? Well, we've already had them. And this is a little grid. This is kind of something I've developed. And these are kind of fun to do. But you still have to know some concepts about work, especially energy. I see PE and KE here, so I'm going to need some information on there, and I see a V over here, the velocity. So what's happening in here, we're taking an object, I'm going to lift it to a height and then drop it. So what we're going to do is figure out the potential energy at each of these heights, and you're actually going to see me doing some calculations on this one. And then as it's dropping, what is the kinetic energy of the object? And then also, what is the velocity of the object as it is falling? So here, okay, kinetic energy, you're probably thinking, I'm going to need mgh. Kinetic energy is 1/2 mv squared, and you're probably thinking, how am I going to do this? Well, we'll get to that a little bit later. And you're thinking, how I can calculate the KE without knowing the velocity? I'll show you. Okay, so we're going to look at the conversion between potential energy and kinetic energy. Remember, in our perfect little physics world, energy is conserved. So what we're going to do, we're going to first calculate the potential energy needed to get to these heights. Okay, where at the beginning there is no potential energy. So to get the potential energy at 10 meters, I'm going to go 200 times 10 times 10 would have, let's see, and I've got 20,000. Okay, now what's going to happen? Let's take it up to 20. And that's 40,000. Now I'm putting a little space here so you can, because sometimes your numbers will get very large. So this kind of keeps, so you can keep track. And there's 50,000. And then 60,000. Then 80,000. And then 100,000. Okay, so we've got our potential energy. So we've got it up to 50 meters, about half the length of a football field or a soccer pitch. And now we're going to drop it. So if you think about it, your teacher might tell you about the PE plus KE equals potential energy plus kinetic energy. So this is going up and this is going down. So if you think about it, at the top, it's got potential energy but no kinetic energy, so that's 0. And so what's happening, the potential energy is, as it's dropping, is being converted to kinetic energy. And you can almost also think of this like a bank account. I've got $100,000 in my bank, and I'm going to start spending it. Remember, I can't be overdrawn, or the bank will get you, and that upsets the laws of physics. And so what we're going to do, okay, we've got 100,000 right here. So we're at the top. How much kinetic energy do we have? We hadn't spent anything, so that's 0. Okay, so it's dropped 10 meters. Now remember that I cannot have use any more than 100,000 joules. Okay, so I need to just subtract the 2, so that's 20,000. And you notice I still got my 100,000 total. Okay, now it's got another one, so we've got 40. And then keep subtracting from the other one. So in this one, we don't really need that equation. You're just doing some multiplying here and then just subtracting here. noticing that when I added these two together, I still have no more than my maximum amount. Okay, and this is the instant before it hits the ground. So not after it's laid there for a while. So you can see, just remember, as you're going upward, potential energy will increase. The kinetic energy, when you drop it, will increase downward. So kind of watch that. So you're probably thinking, how can I do the velocity there? Well, there's two ways you can do this. Now, since I know my kinetic energy, I know V is equal to the square root of 2ke over m. I could use that one. Or, so I can, some people will use that, since that just makes it a little easier. No, you don't have to worry about the subtraction part, because the other one, if I was to, is that V is equal to square root of 2gh, where this h right here is how much it's fallen. Now you can use both of them and still come out with the same number. But on this one, you just got to remember to subtract, because if you use this one like 50, your numbers will decrease, and I don't think it's decreasing its velocity, it's falling. So let's see, at the top, since there's no kinetic energy, it's at 0. Then I've got 2 times 10. I'm going to use this one, then take the square root of that, and I've got 14.1. Usually on this is the nearest tenth to be good enough for most any of your calculations. You can see over here we keep it as whole numbers. We got a lot big ones, so you generally will not have a decimal number. And then let's see, and we after 20, we dropped to 20. It's gone 20. It's at 20 meters per second. And then it's at halfway down. It's 22.4. And now we're at 24.5. And you can see our numbers are increasing, which is what it's supposed to. 0.3, and after it's dropped 31.6, and you can see they're increasing the velocity, which is true, what we wanted. Now, I like this one; it's easier for me, but you might use this one, at least start it out, because you do have to kind of do some mental math, knowing that this h is not the h at where it is, just the height that it's dropped. I'm going to quickly do one more, so if you kind of want to fill in, if you think about it, these three parts will stay zeros. So you can go and get your points there. So I've got a 1,000 object times 10 times 50, and you notice it's got, yes, I know it's not going to be that in the real world, but remember our perfect little physics world, everything is, so we have no air resistance. Okay, I've got 1 million. $3 million. Bank statements look good, isn't it? And then 5. Okay, now we're up to 5 million. Now we're at 7 million. And then okay, so 10 million joules. So all we need to do now is just subtract from the top. So So you can see this one's going to be 3 million, and we're subtracting. And you probably think, do I need to put, no, these are all zeros, so you can subtract these and don't forget to add the zeros after. It makes it easier. There's 7. And there's 9. And there's 9.5 million. And there's our 10 million. You can see that when I added each of these across, I still get my 10 million. So I've reconciled my bank statement. As for the V, remember that's, okay, so that's the first one, 0, 2 times, so I'm going to do the other one, 3 million. 1, 2, 3, 4, and another 0. Let's see. Yep, makes, on these you've got to count your zeros. Just make sure you got them all. Divide by 1,000. And then, okay, 77.5. And then, now we're up to 5. So that's 100. Okay, now we're at 118. Yes, it is not the true fact. A penny will not kill you. It'll probably bruise you pretty good if you dropped it off the Empire State Building, but we're not considering air resistance here. Okay? This is, okay, so that's 137.8, and then the last one, and there's 141.4. Trouble with the calculator. That's probably you heard the banging in the background. These are real simple. Just remember that your potential energy should increase as you go up in height, and then you drop it. The kinetic energy should increase as you go down your column, remembering that these two on each side should equal your total. And then your V, remember there's 2 ways you can look at that. You can use your square root of 2 KE over M to find your V just from your kinetic energy, or V is equal to the square root of 2GH. And just remember, if you use this one, you just got to remember how far it's falling, not where it is. If you use where it is, and what's going to happen, you're going to get your V's will decrease as you go down, and you know that is not correct. Just remember, if you have any questions, feel free to contact your teacher or anybody, or me, or anything like that. Have a good